Okay, so welcome back. It's a pleasure to have Jayadev Athreya from University of Washington, and he'll be talking about variance estimates for geometric counting problem.
Thank you very much. Lots of people to say thank you to. First, I want to say a big thanks to the organizers for putting together this program. Second, a huge thanks to Erez for being willing to switch with me at the last minute. So thank you so much, Erez. And then, I really had hoped that I could be there in person today. Unfortunately, it's didn't work out that to be there in person. It's very nice to see in the audience. I can see you guys now that the camera is zoomed out. I see lots of old friends, and hopefully there'll be people there that I will get to meet at some point who will be new friends. I know this conference is in honor of Professor Dani's 75th birthday. So I want to just start by saying that I was very lucky in my first year of graduate school. Professor Dani came to visit the University of Chicago and gave a series of beautiful lectures on hyperbolic geometry and Diophantine approximation. And at that point, I had very little idea, I think as many of us do when we start in graduate school, of what I wanted to do. And hearing those lectures really brought it home that this is a field of math which ties together many different beautiful things. So you can think about geometry, you can think about number theory, and you can think about things moving around, dynamics, all at the same time and in a really beautifully connected way. So that was deeply influential in what I ended up studying. And so I want to thank Professor Dani for that and wish him many, many happy returns of the day. And I hope this, it's tough to have a 2-week conference in honor of your birthday. You have to stay awake at every single talk. That's not so easy. I won't blame you if you fall asleep though.
Thank you, Jayadev. Thank you.
You're welcome. No, thank you. Okay, so let me start sharing my screen. Let me know if it looks okay. It says screen sharing is paused, resume share. Can you guys see my screen?
Yeah.
Wonderful. Okay. Oh, there's a picture of a cat. That's not what I wanted. Hold on. Let's start here. So as you can see, my nephews had been getting at my iPad. So, okay. So what I want to tell you about today is a story of, which is maybe related to, I know there was a talk earlier today which talked about the lack of mean value formulas and some issues that led to that. I want to talk today about mean value formulas and counting problems associated to 3 different moduli spaces. If that sounds intimidating, don't worry about it. It's not. I'm going to try and make things as concrete as possible. So the game that we're going to study is the following. We have, so cast of characters. We are going to have, and we're going to see this this play will happen in 3 acts. But the cast of characters will all kind of be the same. In all of them, in the sense that there will be defined roles. We're just going to have different actors playing these roles. So the cast of characters will include, let's say, there'll be a moduli space. M will be a moduli space or parameter space, depending on how you like to think about these things, of geometric objects. There will be a map from that space, a map from M to, and I'm going to write this slightly funny looking thing, to the set of, let's say, I'm going to call it sigma of an Rn, where sigma of Rn denotes locally finite atomic measures on Rn. And really, you can think about this really in everything we're going to talk about. These locally finite atomic measures are just going to be, locally finite collections of points. So discrete collections of points. And then you're going to have, so that what you're going to be interested in, so let me take this with us. So one of the nice things that you can't do on a chalkboard that you can do here is you can sort of take this with you. So we have our moduli space and a map from the space to this collection of points. So that is to each M, each point in M, I associate some subset, let's call it, I'll call it lambda sub M in Rn is what I think about it as. And my measure is just, I sum over the elements in lambda M, sort of the associated measure. So sigma M is I think of it as a point set in Rn. And I'm going to be interested in counting problems of the form. I want to understand as M varies in the moduli space, I want to look at the counting problem in particular. I want to understand the counting problem sort of N of MR, which is sort of lambda M intersect the ball of, it's the cardinality of lambda M intersect the ball of radius R. If you think of lambda M as a measure, as an atomic measure, it's just the measure of the ball of radius R. So it's the number of points or the number of things in my set. And in particular, there's a third character, character number 3, which is very important, is we're going to have a sort of a natural measure mu, let's say, on M. And we're going to be interested, so we have some notion of natural, let's say, probability measure. So giving us a notion of a random object in M. And what we want to do is we want to understand, think of picking M from M at random using mu. What can we say about the random variables M n of MR? Again, this is, remember, the cardinality of that counting function. We count the number of objects in this ball of radius R. And what do you mean? What can we say is, for instance, one natural question is, so what can we say about I should really say sequence of random variables as R changes. And the questions about what we can say are, so sorry. I know that this moving around is also a little bit irritating sometimes. So what can we say about these? So the kinds of questions we want to ask is, can we understand expectation? Can we understand, and this talk is going to be about, and so I'll put it all caps, variance. And more generally, can we compare the push forward of mu to the set of, which I'm calling, sigma Rn, to sort of, I'll put in quotes again here, natural point processes in Rn. And before I go into the 3 actual situations we're going to do this, let me just say that this kind of perspective is very influenced by the work, for me, of Bill Veech. And then I don't know if Jens is still there, but even if he's not, I'm going to say this, it's influenced very much by Jens's perspective as well. The idea of taking this kind of collection of points of a geometric origin, this way of associating a random point set in Rn coming from some sort of geometric origin and comparing it to a classical probabilistic object, let's say like a Poisson process, to natural point processes. So for example, like Poisson processes. Okay, now you might be saying Jayadev has come to this homogeneous dynamics meeting and started talking about probability and measures and all this kind of abstract nonsense. So now let me convince you that an audience in homogeneous dynamics and Teichmuller dynamics should care about this big picture perspectives that I'm giving you by introducing the three kind of, if this is kind of the cast of characters, these, there's different ways of performing this play. Let me give you three different ways of performing this play, one of which will be very familiar to this audience, which is the kind of very classical case, which is the space of lattices. So let me start by, let me call it performance one. One is the space of lattices. So I'll also just briefly mention that I'm going to talk about several different pieces of joint work today. This first piece, which you're going to hear about, grows out of joint work that I did as a postdoc with Professor Margulis. The second part is going to be work with Yitwa Chung and Howie Mazer. And the third part, if we have time for it, is going to be joint work with Francisco ARANA HERRERA. And I'll remind you of that as I write things down. Okay, so the space of lattices. So here, my moduli space is going to be Xn is SLNR mod SLNZ is the space. Is there a question? Sorry. Of unimodular lattices in Rn. So I don't need to, usually when I give this as kind of a colloquium talk, I spend a lot of time talking about this identification. I definitely don't need to do that with this audience. And then the assignment I'm going to use is the map. So I'm going to have this map. If I take some unimodular lattice, maybe M is GZN sitting inside of Rn. Already, I just think of my set associated to it, which I called, lambda sub m, is I'm just going to take, I could either take, there's a couple of different assignments. I'm actually going to take, just because it's kind of more natural to generalize, GZN prim. I don't need to put braces around if I write it like that. So I just take the set of primitive vectors in my lattice. And now, let's say and my mu is Haar probability measure on Xn. And now let's say I fix some R positive and I'm interested in N of MR, which is now just the number of points in GZN prim intersect B of 0R. That is, it's the number of primitive vectors in of length at most R in my lattice. I have, of course, due to Siejel, this absolutely beautiful formula, right? If I say Siejel, and this is just a specific case of this, but I integrate over Xn, N of MR, d mu of M, and that's equal to 1 over zeta of N, just the volume, the Euclidean volume of the ball of radius R, right? The expected number of lattice points in the ball of radius R is simply 1 over, primitive lattice points, is 1 over zeta of N times the volume of the ball of radius. So this is a statement about, I claim this is kind of a statement about expectation for a random lattice. And of course, I don't need to spend too much time with this audience talking about this, but maybe I'll just mention that how do you prove this? There's a bunch of different ways you can prove this. You can kind of prove one way is using Fubini's theorem. You can kind of unwrap and rewrap an integral using the fact that if I have Rn minus 0 and Xn over here, there's kind of a common cover I can make of them, which is SLNR modulo, I'll just write it like this, N intersection gamma, And by unwrapping and rewrapping an integral, you can get this formula. But you can also get it in another way. You can say that suppose you believe that n of MR is actually integrable, or more generally, you just take a function on Rn, you add it up over primitive lattice points, and that's now a function on moduli space of lattices. Then, we have, this is of course a special case of sort of integral of f hat d mu n is 1 over zeta of n, integral of f on Rn, where, maybe I'll just put in parentheses, right? F hat of m it's sort of the integral of f d lambda m in some sense, right? It's summation f of v and lambda m. And this is again, so this is expectation of any of these kinds of random variables. Any random variable I get by summing up my function over these lattice points, I can compute its expectation by Siegel's formula. And the way you think about that is f goes to the integral of f hat. So functionals. So f goes to the integral of f hat is a SLNR invariant linear functional on, let's say, continuous compactly supported functions in Rn, means it comes from integration against a SLNR invariant measure on Rn. And there's really only two of those. There's delta measure at 0 and Lebesgue measure up to scaling. And then you do a little work to get what the scaling is by analyzing lattice point count. So that's expectation there. But what about variance in this situation? So variance means here, I need to understand the second moment. So for instance, can I compute the integral over xn of, let's say, n of mr quantity squared d mu of n? And the answer is yes. And this is a beautiful formula of Rogers that's only true for n bigger than or equal to 3. He did claim it for n equals 2, but his formula was, or he claimed a formula for n equals 2, but his formula wasn't quite correct. But it's been corrected by several people since, including, I'll mention, I think it's fairly readable, my former PhD student, Sam Fairchild. This is not the only thing she did, but this is a cool thing she did. She helped correct Rogers for n equals 2. But for n bigger than or equal to 3, the formula has a very nice version. It tells you this thing is equal to, actually, so you get a 1 over zeta of n volume of the ball of radius r. That's the expectation. You get that quantity squared, plus I'm going to say, for right now, I'm just going to say you get lower order terms. So you get the expected value of your random variable squared is its expectation squared plus something smaller. And I don't want to get into the details of the proof here because I want to spend some time getting to the other parts of my talk. But this is a beautiful idea that once again uses this idea of functionals, but now you have to, your space that you're getting functionals on is Rn cross Rn. So you have to be very careful about analyzing what the SLNR invariant measures are. So Rogers computed the variance. What did Margulis and I do? Margulis and I,
Jayadev,
yes.
so you are getting some lower order term. So what will be the variance? Then you subtract that.
Yeah,
square, right?
Right. So the point is that the variance is of lower order than the expectation. It goes to, so if you normalize by r squared, by volume of ball of radius r squared, it goes to 0. In fact, it grows kind of like the volume of the ball of radius r.
Okay.
That's a very good clarification here. So when I say lower order, I actually have very specific information. I can tell you in this particular case exactly what it is actually. By the way, just as a recommendation, and I think maybe Barak would probably echo this, if you ever want some very interesting reading, there's an amazing book by Rogers called Packing and Covering. which I really recommend. It has a ton of fascinating ideas in it. He also, maybe I'll just make a quick, interesting historical remark. Many of you maybe have heard me make this before, but Rogers proves this formula by actually computing integrals on the space of lattices. How does he compute these integrals? He says, oh, I'm going to compute an integral over a torus, over a set of matrices that basically looks like a torus, like an n-dimensional torus. And then I'm going to push, which is actually in our language would correspond to a horosphere. And then I'm going to push it around by a diagonal flow, and I'm claim that these integrals converge to the integral over the full space. And Rogers says something like, I have a proof of this fact, which I don't intend to publish, but that's how I'm going to compute these integrals. So he's claiming an equidistribution of horospheres in the space of lattices. This is in 1955. Though I don't think he would have necessarily called it that, but that's exactly what he's claiming. And I don't think it's unreasonable to think that he did have a proof. I think you could do that particular equidistribution without all of the technology of ergodic theory and dynamics. Though I'd be happy to hear different from other folks in the audience of what they thought of Rogers' claim. Okay. Anybody have thoughts?
I just want to, we've discussed this before, but maybe the audience will be interested. So I think the more correct thing to say is he had a equidistribution of horospheres evaluated against functions which are
Siejel transforms.
Siejel transforms, which sort of changes the problem somewhat, and you can somehow do it using Fourier analysis. And there's a paper that came out in the 70s of Bourgain, where he calls something like this the Rogers-Davenport lemma, and he gives a proof using harmonic analysis. So, and also, well, there's a question of whether you average along the AT direction or not. I think in Bourgain you do. So
yeah, and in Rogers's book, he actually does extra averaging, and I think maybe even comes close to a proof there. But in the paper, he claims it without extra averaging. In the paper in 1955, he claims it without extra averaging. Thanks, Barak. Okay, maybe I'll just mention a quick application of this. Why did I start to care about these kinds of questions, this variance question? There's an application, and I'll just say, motivated by a problem in unipotent dynamics, in dynamics of unipotent flows. Flows on Xn, Margulis and I showed the following result, which I quite like. It says the measure of the set of M in Xn, where the lattice, the primitive vectors in the lattice, or the lattice itself, in fact, does not intersect a particular set A, so A is just some subset of Rn, which is measurable, is less than or equal to, there's an explicit constant over the n-dimensional volume of A. So this has no restrictions on the geometry of the set. We called this a kind of random Minkowski theorem. We said, oh, what's the probability of nothing in this set? We know the expected value is the measure of the set. So the probability that you have nothing is certainly, it's kind of a concentration inequality. We say, oh, let's bound the probability that we have. We can even just bound the probability we have too many or too few. The fact that the probability that the random variable is far away from its mean, well, that's controlled in terms of the variance, and that's how you get this kind of bound. So this is a kind of sometimes called a concentration inequality. So, and then we also, we had other results. We harvested this for a while. We got results about values of polynomials at lattice points. We had other applications to Oppenheim, almost surely in terms of heights of solutions of setting a quadratic form to being close to zero, and so on. But all of that flowed from this idea of estimating this variance. So the point is, understanding this variance really gives you a lot of interesting information about specific problems about these sets, lambda m. Okay. So act 2, maybe I'll pause here, or not act 2. These are 3 different plays I claimed, or 3 different productions of the same play. Production number 2. But maybe as I'm writing this, I'll ask, are there some questions about production number 1? I didn't want to spend that much time on that actually, because in some sense it's setting the stage for these next things. That it's what motivated these next projects. Okay, thank you for letting me go on to the next ones. You can always ask about lattices at the end. I'm very happy to answer questions about lattices at the end. So production number 2 is M is now going to be the moduli space of translation surfaces. So let me very quickly tell you what a translation surface is. So this is kind of another generalization of X2, which is SL2R mod SL2Z. So of course the previous generalization we talked about was the space of lattices in higher dimensions, where we just replaced the 2 with an n. But this is, I think of GSL2Z, right, as identified to GZ2, which I'm going to think of also as identified to R2 mod GZ2, which is, I take my columns of G and I have a parallelogram with parallel sides identified. These are, maybe this is G is equal to, let's say, UV, this is U and this is V, and I get a torus. So now what I do is I say, take a polygon with parallel sides identified by translation to form a compact Riemann surface. So there's a bunch of things going on in this definition where when I say identify parallel sides by translation, I mean implicitly that my polygon every side has a parallel side of the same length that I can identify it to. So let me just give you an example here. Let me take, let's say, an octagon. And there's cultural differences in the translation surface community. Do you draw an octagon or do you draw an L as your first thing? I always like drawing the octagon for some reason. And I didn't do a hexagon. You might say, oh, well, you started with a fourgon. Why wouldn't you go to a hexagon? Maybe I'll say an exercise. Hexagon also leads to a torus. And that's a nice exercise to do. If you do this and you identify opposite sides, let's see what happens to this corner. This corner is glued to this corner. Well, that's the bottom of 3. It's glued to the top of 4. It's glued to the bottom, sort of bottom right of 1. It's the left of 2. It's the top right of 3, and it's the bottom of 4. All the 8 corners collapse to 1 point. And you can kind of see what surface you're going to get. You can sort of complete the square here. And this is not part of your surface. You can identify opposite sides of that, and you'd get a kind of, let me go back to white. You'd get a torus, and you'd get this kind of yellow hole in it. And you have these 4 pink corners again. And now you have to identify opposite sides of this hole. And what you get is you get an extra handle coming out. And I'll just sorry. This is drawing in real time is tricky. So you get a kind of an extra hole, and you get that this pink point on the surface has angle. Let's see what the angle will be. The interior angle of an octagon is 3 pi over 4. So you get an angle of 6 pi here. You can also see that as you have 4 3 pi over 2s. 8 times 3 pi over 4. So in general, what you get is you get a genus G Riemann surface, because everything we're doing, gluing, is holomorphic. The translations are holomorphic. you also get a holomorphic, I don't know why I wrote an arrow, plus a holomorphic one form, call it dz, because just observing the fact that d of z plus c is dz, right? This is a calculus exercise. So what it means is when you have a surface like this, you can talk about what it means to go up, what it means to go to the right, and you can talk about how far you went using this, right? A one form eats curves and spits out numbers. This is dz, so it eats curves and spits out a complex number, which tells you how far you went and what direction you went in. And the set we're going to be interested in, we're going to be interested in what are called saddle connections. Saddle connections are straight line trajectories connecting points with too much angle. So there will always be points with too much angle as soon as the genus is bigger than or equal to 2, because as soon as the genus is bigger than or equal to 2, your surface has to have negative curvature. And so if you flatten it out, you've got to put the curvature somewhere, and the curvature is going to this finite collection of points. In this case, the case we drew, there's 1 point. Maybe I'll just give you a little exercise for the grad students in the room. A 4G gon, and I say a regular 4G gon, leads to genus G surface with 1 point with angle 2 pi times 2g. Oh, sorry, not 2g. 2g minus 1. And a 4g plus 2 gon leads to a genus G surface. Genus G surface with 2 points with angle 2 pi g each. And I can say a little bit, if you want to ask at the end, there's a relationship between the order of the one form. These points with excess angle correspond to zeros of the holomorphic one form, and the order of the zero and the order of the excess angle are related just basically by dividing by 2 pi. But for right now, what I want to just say is we have, I want to just be kind of heuristic. So when I claimed that M was going to be the space of these translation surfaces, I'll call them TSs, with fixed orders of excess angle, or orders of zeros of one form. And now remember, a saddle connection gamma was a trajectory connecting points with too much angle. Associated to each gamma is going to be what's called its holonomy vector, which is integrating the holomorphic one form omega coming from dz. So z gamma is the integral of omega over gamma. It's a complex number that tells you how far you went horizontally and how far you went vertically, or what direction you went in and what length you are. And so lambda sub m is going to be the collection of z gamma. Gamma is a saddle connection on my surface little m. And now what is mu? So again, let's go back to this octagon picture. I drew up or attempted to draw a regular octagon. I clearly didn't, actually, so that's already kind of good. What you really need for this octagon is you need 4 vectors, 4 complex numbers. And they should satisfy some mild non-collinearity condition, but really it's some open dense set in C4. So this is kind of a natural, this is a big lie, but C4 is kind of like M. That's not really true because I want to consider the equivalent of unimodular things with unit area. So I really want to sort of quotient out by kind of an R star action here. And that's not a terrible lie. And now to talk about the measure, let's think about how would you build Haar measure this mu n or this mu on xn from scratch? Well, you would say, oh, I just take Lebesgue. I think about here, maybe I'll just draw a picture here. So here is kind of the so this is area positive surfaces. And now this is kind of area 1 surfaces inside. And what I do to understand the measure of a set here, maybe this yellow set here, is I make the cone over it and I take the area of that cone or the volume of that cone. And that's exactly how you build Haar measure on SLNR. You think about SLNR as sitting inside of n by n matrices. And you take this cone measure, and that is an SLNR invariant measure on SLNR. And so this is an exact analog of that. My students always joke that I draw the n equals square root of 2 picture because I draw a picture with 2 dimensions here. The measure here, this is called Mazur-Smiley-Veech measure, or some people call it Mazur-Smiley-Veech measure. It's a topic of some discussion. Some people call it Lebesgue measure. Some people call it Mazur-Veech measure. We can get into the history later. And here's what's cool is I didn't tell you, but there's an SL2R action on the space M, just coming from taking your polygon and hitting it with the matrix. And the way I at least mentioned on how to build the measure, which is to say take Lebesgue measure in the sides, essentially. That's clearly SL2R invariant because SL2R preserves Lebesgue measure on R2. What's much harder, and a theorem of Mazur and Veech independently, is that this measure is finite and ergodic. That's a deep and important theorem. Okay, but now let's talk about what I came here for, which is so now we have M goes to lambda M. We have n of mr, which is counting lambda m intersect b of 0 r. And we have the first question, which is expectation, which is if I integrate n of mr over my space M d mu, what do I get? And here is a beautiful theorem of Veech. It's called the Siejel-Veech formula, which says that the integral of n of mr d mu over M is equal to, there's a constant depending on the moduli space, times just the, times pi r squared, the volume of the ball of radius r in C. Veech proved a more general version. Again, you can say take f, which is a continuous compactly supported function on C, define f hat of m to be the sum f of m, let's say z in lambda m. Then the integral of f hat d mu over m is the cm integral over f integral over c here. So again, and the reason I wanted to mention that functional idea when I talked about lattices is a very similar, that's exactly the idea of the proof here. You can use f goes to the integral of f hat. If you believe f hat is integrable, then that's a linear functional. And so there is this constant. And these constants are, I'll just put it this way, they're very interesting. By the way, especially for the students in the room, I'm going over an enormous amount of material quite fast. I realize that. The idea is, with this talk, is I hope you see some parallels between something you might know reasonably well already, the space of lattices, and things that you might want to know more about, the space of translation surfaces. And please feel free to reach out to me or to other folks in the room about what are some resources that might be useful to learn about translation surfaces. Yeah, there's maybe I'll just mention here, there's several articles in the Handbook of Dynamical Systems from about 20 years ago, which are really excellent. And there's more recent surveys as well, but work of Eskin and Mazur and Hubert Schmidt. There's some really nice surveys if you're interested in this. So the goal is to kind of get you interested in this by saying, hey, look, there's all these interesting parallels. Okay, what about variance? So I'll just say that in the interest of getting to the third act, because I did want to say the third act, I proved with Yitwa Chung and Howie Mazur that N of MR has finite variance. In general, we show that F hat is an L2 of M mu Mazur-Smiley Veech in fact, we prove L2 plus a little bit extra depending on the particular moduli space for compactly supported functions. And I should also mention that this has been recently extended by Etienne Bonafou to all SL2R invariant measures on M using in a crucial way work of Ben Dozier. So there's active work going to say, oh, it's not just this probability measure, but there's other probability measures, other random variables you can get, and those also have finite variance. Okay. And I'll just mention an application of this that we just finished this year with Fairchild and Mazur, is we used this used ACM plus ergodic theory of almost Neveu's, who some of you heard from earlier, and an argument of Eskin-Mazur, and ideas from a paper of Neveu, Rohr, Weiss actually all helped us clarify to count pairs of saddle connections. I'll also mention, so Neveu, Rohr, Weiss can be combined with this, with our finite variance ideas, to get effective counting of pairs. And that strategy was executed very nicely by Etienne Bonafou. And maybe I'll just say, I don't want to get into the details of this counting pairs problem, but the motivation for that was, again, trying to understand kind of correlations of saddle connections. And this thing I mentioned at the beginning of the talk of comparing things to a Poisson process. Saddle connections aren't a Poisson process, but they're, how you quantify that is an interesting idea. So I have 5 minutes left. So obviously I'm not going to get through the, do I have more than 5 minutes left?
Actually, you have 15 minutes, I think.
Oh, perfect. Great. So I can say a lot more about case number 3 then, because I do want to spend some time talking about the third act, but maybe I'll pause before I talk about the third production of this play and ask, I know I went through that second production very, very fast, right? It felt probably like experimental theater than any kind of narrative. But maybe I'll pause and ask for some questions. I know it was sketchy, but if folks have questions, I can pause before going on to hyperbolic surfaces. Okay, as you might guess, this talk was originally planned to be a mini course when I was going to be there in person. And I made the probably unwise decision of trying to say what I was going to say in 3 hours and 1. So I'm sorry. I just like this a lot. And I'll also say that these are problems I've been thinking about for the last 15 years or so. And it's funny to think that they're all kind of, I didn't realize that they were all kind of very similar problems until pretty recently. So I like presenting it this way. The downside is you see the parallels, but you might not see the details in each particular performance. Okay, so let's go to performance number 3. So now we're really going to get into the realms of experimental theater, because there's going to be something that wasn't present or something that was present in the first 2 acts or the first 2 performances, which was a group action, is not going to be present here. We're going to have, in both of those, at least to compute the expectation, we use the action of the group either SLNR or the group SL2R. Here, we're not going to have a group action around for expectation. But let me tell you what so the play is really different in some sense, but the setting is very much the same. The plot is kind of similar. You just don't have all of the same ingredients. So now here, M is, I'll say MG, the moduli space of hyperbolic genus G surfaces. In particular, this is also a generalization. Well, it's a generalization of kind of, SO2 mod X2, which is H2 mod SL2Z, which is the space of flat tori. This is the space, which is the space of constant curvature metrics on a genus 1 surface. So this is now, I'm going to think about G being bigger than or equal to 2. So now we're thinking about constant curvature metrics on a genus G bigger than or equal to 2 surface. Those metrics have to be hyperbolic by Gauss-Bonnet. So M is MG, moduli space of hyperbolic surfaces. And now, given a hyperbolic surface, my lambda M is now a subset not of R2, but is going to be a set of the positive reals, is the set of length of gamma, where gamma is a simple closed geodesic, SCG, simple closed geodesic, on my hyperbolic surface little m. So I look at the set of lengths of simple closed geodesics. And now my function n of mr is just the number of geodesics gamma, a simple closed geodesic, with L of, maybe I'll write L, usually, so in hyperbolic, L gamma of M is how you usually write it, is less than or equal to R. So you think of gamma as being fixed and your metric M is varying. And here, MIRZAKHANI, I didn't tell you what the measure was. Sorry, I need to tell you what the measure is. And mu on MG is what's called the Weil-Petersson metric, Weil-Petersson measure, volume on MG. So this is a measure that very crucially uses the hyperbolic lengths of curves in its formula. You take a pants decompose, you decompose the surface into sort of basic building blocks, what are called pairs of pants. So you have your genus G surface, maybe I'll just draw a genus 2 surface. And then you cut it up in this case into, let's say I'll draw one obvious decomposition. This is now 2 3-punctured spheres, or 3 spheres with 3 boundary components. Sorry, ignore that bottom curve there, and then you have, right? You have these two 3-punctured spheres, and for each of these curves, you have a length parameter and a twist parameter. So the length parameter, of course, the lengths have to be the same, but when I glue them, I can twist them, and that twist belongs to the is between 0 and the length. And the measure is basically, it's very closely related to DLI wedge D tau I. There's a deep theorem because you should be asking all kinds of questions. You say, what do you mean that's a measure? One, what's kind of the moduli of 3 spheres with 3 boundary components? The answer is all the modulus, all the information is there. It's just the length of the boundary component that tells you what the hyperbolic metric is. But the fact that this quantity does not depend on the particular decomposition you choose is a deep theorem of Wolpert's. It's sometimes called Wolpert's magic formula. And it really is pretty magical. But you can think of it this way, just very similar to what we said about translation surfaces, kind of Lebesgue on sides. It's not Lebesgue on sides, but it's like, you cut it up into simple pieces and it's Lebesgue on lengths, very vaguely speaking. And here is a beautiful, beautiful result of MIRZAKHANI is N of MR has finite expectation, and the expectation is a polynomial of degree r to the 6g minus 6 of degree 6g minus 6 in R, and the coefficients can be computed in terms of intersection numbers on moduli space. It's really, I mean, an absolutely stunning piece of work. The finite expectation is not the hard part. The hard part is everything else I said here. But there is something very interesting, which is MIRZAKHANI also proves that N of MR is in L2 minus epsilon of M mu, and that it is not in L2 plus epsilon of mu for every epsilon positive. So it's not, doesn't have more than a second moment, but it has every moment less than a second moment. So of course, the question that you want to ask is, does it have finite variance? And so this is what I proved with Francisco ARANA HERRERA, who is now a postdoc at Maryland, fabulous young mathematician. And what we proved is that N of MR is in L2 of M mu. And then we used this to get, again, counting results for pairs of curves on surfaces. And I'll maybe just say that we are in work in progress, something that I'm pretty excited about. We're working to try and use this with and Mark Bell to try and understand the distribution of another kind of geometric quantity. We're looking at, you take gamma 1, gamma 2, simple closed, gamma 1, gamma 2, simple closed geodesics on M. We want to look at the kind of normalized intersection number, what we're calling the pair correlation of these curves on M and maybe length less than or equal to R. We look at these kind of normalized intersections, and we're trying to understand what the limiting distribution of that kind of distribution on R is. So saying, if you take two curves and you look at their intersection number, your first guess is that it will be the product of the lengths. That would be your first heuristic. How good is that guess? And we're using, we're trying to use, we're trying to get some information on this. I think this is probably a good place to stop. Again, like I said, let me make clear that my goal for this talk was not that everybody understand every single part of it, but rather that you would be intrigued by the parallels to see either some questions in any of these situations motivated. Maybe you know one case better than the other. Maybe you could port a question over from one case to the other. The other thing is, if you see other situations like this, I think there's a list of natural questions you could look at of what are expectations, what are variances, what are higher moments? Is there a moment generating function for these kinds of assignments? If so, can it help you compare these kind of random assignments to things like Poisson processes? Is again like the larger ulterior motive here. So I think this is a good place to stop, which leaves us 4 minutes for questions.
Questions, comments?
So in this last work with ARANA HERRERA, you've jumped from L2 to pairs. So I'm assuming the count of the curves themselves is Mirzakhani, right?
That's right. That's
and
right. Thank you.
So
That's a
and-
good
and-
point.
And that was effectivized recently. So you could probably could you effectivize the count using this technique and effectivize the count for pairs using this technique? Is my question.
Possibly. So maybe I'll just say that we using L2 in the translation surface setting, Renee, I mean, as you know, Renee and I wrote this appendix to our paper where we could get effective, just using L2, we could get effective along a subsequence. We could recover your guys's bound along a subsequence in some sense. Very sparse subsequence, lacunary subsequence. It's an interesting question to see if you could use, like you're thinking of these new Eskin, Mirzakhani, Rafi results on the effectivization of counting, of Mirzakhani's counting, and seeing if you effectivize that with pairs. That's interesting. I hadn't thought of that, but it may be possible. I don't know is the answer, but that's a very interesting question. To be frank, I don't yet understand their proof because I know it uses exponential mixing of the Teichmuller flow, but I don't understand exactly how they use it to get to effectivize Mariam's count.
Any more question? If not, let's thanks the speaker again for this wonderful talk.
And I'm very happy to share the slides for whatever they're worth. And if you have questions, further questions, you can send me an email and all of these papers are now at least on archive, if not published. So you can take a look at those as well.
Thank you. So we meet again at 2 o'clock.
Enjoy your lunch and break, everyone. Bye.